Most stars die a quiet death, but massive stars typically die in spectacular supernova explosions. Left behind are astounding objects of incredible density.
A supernova is the last gasp of a star's evolution when in the core of the star it runs out of hydrogen gas. The star basically collapses and has this extraordinarily violent explosion. We believe, theoretically at least, leaving behind an extremely compact object with a mass comparable to that of the Sun that can be spinning extremely rapidly. It'll be an object maybe only 10 or 20 miles in diameter.
In the context of the death of massive stars, we still don't understand the physical process that ejects the outer envelope. We know the core is left behind as a neutron star because we see it.
What we know of such exotic celestial bodies as neutron stars, pulsars, and black holes began with a single event, witnessed almost 1,000 years ago.
The ancient Chinese kept a very close watch on the sky because they felt that astronomical phenomena had sociological significance. In other words, they were astrologers. And on July 4, 1054, the then court astronomer recorded the appearance of what they called a guest star, blazing out in a part of the sky that we now call the constellation Taurus. He said that it was visible by day like Venus for about 2 weeks, and after more than a year it gradually became invisible. That's a very impressive blaze, something that's visible by day like Venus. And for a star to take as long as more than a year to fade below naked eye visibility is also very impressive.
The Crab Nebula, which has been known for a couple of hundred years as an astronomical object, is called the Crab Nebula because the nebulous filaments that are luminous that one sees through a telescope resemble that of a crab. And from astronomical observations of this nebula, you can see that it's expanding. You can see the gas is moving out. You can measure the velocities of that gas.
In 1933, Fritz Zwicky, a Swiss-American astronomer, and Walter Baade, a German-American astronomer, suggested that the supernova phenomenon was a result of a collapse of a normal star to a neutron star.
The neutron stars are called neutron stars because we believe that they're primarily made out of neutrons, which are components of the atomic nucleus. And in fact, the density of a neutron star is very close to the density of the nucleus of the atom. And this is the most dense material known in the universe.
So, while less massive stars eventually collapse into white dwarfs, supported by the pressure of their own electrons, high-mass stars overcome that pressure to collapse at their cores into neutron stars.
The dense neutron star at the center, which had been left over by the explosion, was still unseen, and astronomers, in fact, didn't expect to see it. A ball of gas only 14 miles in diameter has to be impossibly hot to produce enough light to be seen from the Earth. And so astronomers didn't believe it could be that hot and didn't believe that they would ever see it.
With no hopes of ever observing a neutron star, astronomers did not actively seek them. Their eventual discovery came as a total surprise.
In 1967, a British graduate student named Jocelyn Bell was carrying out her thesis research with a telescope which was designed to observe radio waves from space. And she noted on the records of the telescope regular pulses of radio waves coming from a particular spot in the sky. They recurred every night at the same spot. She thought for a while about them and couldn't understand where these regular pulses were coming from. There were no known sources of radio waves that produce signals so well defined and so regular in their occurrence. And so for a while, she and her thesis advisors thought that perhaps they had detected the first signal from an extraterrestrial civilization. They called the source the LGM because they thought it might be coming from little green men. When they discovered a second and a third and then a fourth source, like the first, coming from different spots in the sky and pulsing at different rates, it became clear that they were looking at something natural, but they didn't quite understand what it was. They published their results, and astronomers called these new radio sources pulsars, for pulsating radio sources.
With a little bit of thought, they recognized that these extraordinarily periodic phenomena were most reasonably explained as being due to the rotation of some astronomical object. And on theoretical grounds, people soon realized that these objects were likely supernova remnants, so-called neutron stars, the burned out core of an exploding star.
Well, the exterior of a neutron star is dominated by its very intense magnetic field. And this intense magnetic field, as it rotates, appears to generate streams of charged particles, probably electrons and positrons. And what we see typically is the radio waves emitted by these streams of charged particles. These radio waves appear to be emitted rather like a lighthouse beam. And much as when we see a lighthouse from a distance, it seems like the light is flashing at us, in fact, the lighthouse beam is continuous and it's rotating and illuminates all of the region around it, but at different times.
To confirm the hypothesis that pulsars are indeed rapidly spinning neutron stars, astronomers knew they must find one in the center of a supernova remnant.
It was known that the Crab Nebula was a supernova remnant, and so it was an excellent place to look for a possible pulsar.
I think the most exciting observation that I have ever made personally was of the pulsar in the Crab Nebula. The Crab Nebula is the result of the supernova explosion, which was observed in 1054 AD, and it was discovered in the late 60s that there was a radio source that was beeping 30 times a second in the center of the Crab Nebula. Working with my colleague Joe Wampler, we devised a system that allowed us to take a picture of the center of the Crab Nebula with a spinning disk that allowed it to work like a strobe light and freeze the rapid flickering of this pulsar. And we saw right in front of our eyes on the TV screen this pulsar just pulsing away at us. And it was a very exciting moment because instantly we knew which object in the Crab Nebula was the pulsar, which star, and that in fact it was pulsing in the optical just as it was in the radio. And it was such a graphic, immediate demonstration of some scientific result that it was extraordinarily exciting.
At the time, the Crab pulsar was also unique and really, I think, had the most fascination to us at the time because it was far and away the fastest known pulsar. Most pulsars were rotating with periods of a few seconds to a few tenths of a second. Here was something that rotated 30 times a second. Since then, amazingly enough, people have found pulsars that pulse up to about 1,000 times a second.
A black hole is one of the strangest stellar remnants that we can possibly imagine. How does a black hole form? You take a star, a very large star. When it finally finishes its life cycle, it gets so small, compresses down to such a small size that nothing can get away from it, not even light. And once an object has compressed so much that nothing can get away from it, not even light, we call it a black hole. Why? Because you can't go faster than the speed of light. So if you get too close to it, abandon hope, all ye who enter here. You get too close to a black hole and you aren't going to come out again.
It is quite probable that the formation of a black hole from an extremely massive star need not be preceded by an observable supernova event. If the iron core that begins to collapse is too massive, and if too much material follows the collapse and does not rebound with sufficient energy, then the rebound essentially stalls it can go out part way, but gravity will eventually take over and suck the material back in. This will give rise to the formation of a black hole without producing an observable supernova.
When a black hole is formed from a dying star, the boundary, the event horizon that it creates is only 10 or 12 miles from the center. The black hole is a very tiny object, and the black hole attracts matter to it only due to gravity. Black holes are not vacuum cleaners in space. They don't go around sucking things up with more power or other effects besides their gravitational force.
We are not entirely certain, based on the observations, that black holes even exist. I would say that the observations lead us to conclude with greater than 99% certainty that black holes exist and are the remnants of extremely massive stars, but we have never actually witnessed the formation of a black hole.
So astronomers began searching for the elusive black hole. But among the brilliant stars of the galaxy, how could they detect a relatively tiny object that emits no light?
In particular, you can have a black hole in a binary system, and it will exert exactly the same force on the companion star as a normal star of the black hole's mass, and the normal star will be seen to be going in orbit around something that is not a source of visible light. And this was predicted as the right way to find black holes, as well as neutron stars.
If a black hole, for example, is in a binary star system, then the black hole will pull matter from its companion into itself. However, a black hole is typically 10 miles across or so. It's very small. And therefore, when it pulls the matter from the other star onto it, that matter can't all fall in at once. The matter from the companion has to wait its turn, just like water going down a drain. So as the matter from the companion swirls round and round and round the black hole waiting to go down into it, other matter from the companion star is pouring onto this region. There is created a disk around the black hole called the accretion disk of matter waiting to get in.
But when it goes down the tubes, it gets very hot. And so in the process of disappearing, it radiates X-rays. And you recognize a black hole binary because it's an X-ray source, so you know there's something compact there, and the mass of the X-ray object is too big for a stable neutron star.
If the X-rays are emitted by the gas before the gas enters the black hole, before it crosses the event horizon, then those X-rays can escape. So if we look at a list of objects that are producing X-rays, some of those objects might be black holes swallowing matter, and so that's a way to search for black holes.
Probably the most likely black hole candidate is in the constellation Cygnus, the Swan, and it's called Cygnus X1, meaning it's the first X-ray source that was discovered in Cygnus.
When the optical identification was made, many astronomers did spectra and found that indeed it was a binary star with a period of about 6 days, and that the velocity amplitude was so large that the mass of the companion object was at least 3 or 4 solar masses and probably 6 to 10. In other words, it was in the black hole class, not in the neutron star class. And Cygnus X1 is still the best established of the black hole X-ray binaries. There are now 3 or 4, maybe 5 or 6 other systems for which you can say it's compact and therefore it must be a neutron star or a black hole, but it's too massive to be a neutron star, therefore it's a black hole.
Even though evidence of incredibly compact objects can be observed, their theoretical implications defy imagination.
The speculation that one might be able to go inside a black hole through and re-emerge somewhere else in the universe or in the distant past, that speculation was actually based on an exact solution of Einstein's equations of general relativity that describes such a thing. However, despite that basis in Einstein's equations, no theoretical physicist believes that this is possible.
Unfortunately, when you talk about real black holes, it does not appear possible to be able to do it. So not even the pieces of the spaceship would survive. And it's also true that as you get too close to a black hole that you make from a star, you get about 1,000 miles away from it, and the tidal gravitational forces are going to do very strange things to people. If you imagine yourself falling feet first, you're going to get stretched out because your feet are closer to the black hole than your head is, so they're going to tend to be pulled towards it faster. But you're also going to get squished together because your two shoulders are going to fall towards the hole on converging paths. So we can find these kind of torture instruments in the dungeons of places like the Tower of London. They had the rack and the straitjacket, and in a black hole you get put in the rack and the straitjacket at the same time. So for most realistic black holes you would have spaceship parts and astronaut parts. No, I don't want to go exploring a black hole that way.
The death of massive stars marks the beginning of the strangest of celestial objects: neutron stars, pulsars, and black holes. Our quest to understand these objects challenges current laws of physics and pushes the frontiers of astronomy.